Welcome. Today we solve LeetCode 3720, lexicographically smallest permutation greater than target. We will rearrange the letters of string S to beat string target in dictionary order. And among all winning rearrangements, we want the smallest one. If it is impossible, we return empty. Let's build the idea from zero, slowly. The goal. You are given two strings, S and target, with the same length. You may only rearrange the letters of S, that is a permutation. Return the lexicographically smallest permutation of S that is strictly greater than target. If no permutation of S beats target, return an empty string. Same letters as S, only the order can change. What is a permutation? It means the same bag of letters in a different order. For S equals ABC, the permutations are ABC, ACB, BAC, BCA, CAB, and CBA. You cannot invent a new letter. You cannot drop a letter. Character counts must match exactly. Lexicographic order is dictionary order. Compare two same-length strings from left to right. At the first position they differ, the one with the later alphabet letter is greater. So BCA is greater than BBA, because at position 1, C is greater than B. And EELT is greater than CODE, because at position 0, E is greater than C. Strictly greater means they are not equal. We must win at some first difference. Example 1S is ABC. Target is BBA. All permutations in order ABC, ACB, BAC, BCA, CAB, CBA. The ones strictly greater than BBA are BCA, CAB, and CBA. The smallest among those is BCA. So the output is BCA. Notice, we do not want the overall smallest permutation. We want the smallest one that still beats target. Example 2S is LEET. Target is CODE. The overall smallest permutation of LEET is EELT. That already beats CODE at the first letter because E is greater than C. So the answer is simply EELT. Sometimes the sorted arrangement of S already wins, and that is optimal. Example 3. S is BABA. Target is BBAA. All permutations are AABB, ABAB, ABBA, BAAB, BABA, and BBAA. The largest is BBAA, which equals target. Nothing is strictly greater, so the answer is the empty string. Constraints. S and target have the same length. NN is at least 1 and at most 300. Both strings use only lowercase English letters. Because n can be 300, listing all permutations is impossible. N factorial explodes. We need a smart build with letter counts and a greedy idea. Why not list every permutation? Even for n equals 10, that is millions of strings. For n equals 300, it is impossible. Instead, count how many of each letter we have from S, then build the answer one position at a time from left to right. Core strategy. 1. Count letters in S. 2. Build left to right, trying letters from a towards Z, smallest first. 3. While we are still tied with target, only place a letter that is greater than or equal to target's letter at that position. 4. The moment we place a letter strictly greater than target's letter, fill the rest with the remaining letters in ascending sorted order. The first success is the lexicographically smallest answer. 2 modes. Tight means so far our answer equals target's prefix. Then the next letter must be at least target's next letter. Already greater means we already placed a bigger letter earlier. Then we no longer care about target. We just dump the remaining letters in a 2Z order to keep the ending as small as possible. Strictly greater is 1 at the bump position. The bump move. When still tight at position I, you have two useful ideas. Option A, place exactly target of I if you still have that letter and stay tight. Option B, place the smallest letter you own that is greater than target of I. Then you win and you append remaining letters sorted ascending. Prefer the smallest bump letter that works. Dry run of example 2. S is LEET. Counts E2, L1, T1. Target is CODE. At position 0, we are tight. Target wants C. We do not have C. The smallest available letter, at least C, is E, and E is greater than C. Place E, we are already greater. Fill the rest sorted, ELT. Result EELT. Done. Dry run of example 1. Start. S is A, B, C. Counts, 1 each. Target is B, B, A. Position 0, tight. Target wants B. Skipper, because A is less than B. Place B equal to target, stay tight. Remaining letters, A and C. Matching B keeps the prefix as small as possible. Continue example 1. So far we have B, remaining A and C. Target's next letter is also B. We cannot place A, because A is less than B. Place C, which is greater than B. That is the bump. Fill the rest with remaining letters sorted, just A. Result B, C, A. That matches the expected answer. Dry run of example 3 failing. S is B, A, B, A. Counts, a 2, B, 2. Target is B, B, A, A. If we stay equal the whole way, we build exactly B, B, A, A. But equal is not strictly greater. There is no way to bump to something larger using only these letters. The maximum permutation is B, B, A, A. So we return empty. Algorithm steps. 1. Build a frequency count of letters in S, size 26. 2. Build at position I with a tight flag. 3. Try letters from a 2Z that we still have. If tight, skip letters less than target of I. 4. If the chosen letter is greater than target of I, place it. Append remaining letters sorted ascending. Success. 5. If the letter equals target of I, place it and continue still tight. 6. If nothing works, return empty. Why sort the tail after a bump? Once we place a letter greater than target at the first difference, the whole string is already strictly greater, no matter what follows. To keep the full string lexicographically smallest, the suffix must be the smallest arrangement of leftover letters. That means sorted ascending, A towards Z. After bumping with E, leftover E, L, T becomes E, E, L, T, not a larger scramble. Code sketch idea. Keep a counter of letters. Depth first build at index I with tight, true or false. If we finish the string, we succeed only if we are no longer tight, meaning we already became greater. For candidates, if tight start from target's letter, else from A. Decrease the count, try the letter. If we are already greater or this letter bumps above target, append remaining sorted and return success. If we stay equal, recurse. Undo the count on failure. Trying letters from small to large makes the first success the smallest answer. Why sometimes stay equal? Bumping too early with a much larger letter can make a worse, larger answer. Matching B at the start, then bumping later can beat starting with C, because B is less than C. So the search tries smaller letters first, including staying equal when that letter is available, before trying bigger bumps at the same position. Edge cases. If n is 1, the answer is the single letter of S when it is greater than target's only letter, otherwise empty. If all letters are too small to bump anywhere, empty. If the sorted permutation of S already beats target, that sorted string is the answer. Duplicates are allowed, like 2 E's in LEET, so always use counts carefully and never go negative. Common mistakes. Computing the next permutation of target. Wrong, because letters must come from S. Returning any permutation greater than target instead of the smallest. Allowing the answer to equal target. It must be strictly greater. Messing up duplicate counts. And after a bump, filling the tail in descending order instead of ascending. Complexity. With the bump and fill idea, time is about O of n times 26. Each position tries a handful of letters, and when we bump, we finish the suffix in linear time. Space is O of n for the answer plus O of 26 for counts. That is comfortable for n up to 300, far better than generating n factorial permutations. Takeaways. We want the smallest permutation of S that is strictly greater than target. Use letter counts. Never invent letters. Build left to right, while tied with target, only place letters at least target of I. On the first bump, fill remaining letters sorted to Z. If no construction works, return empty. Match as needed, bump once, sort the rest. You got this.